In the last videos, we have presented the global CO2 emissions from transport. Slightly over 45% of emissions come from road and passenger transport, followed by freight at around 29%, then aviation and shipping. In this video, we will dive deeper into the freight sector. Zero-emission, heavy-duty vehicle technology to support decarbonization of the freight sector has been a very hot topic in transportation. Electric drive heavy-duty vehicle technologies are essential to fully decarbonize the transport sector. Heavy-duty freight trucks are disproportionate contributors to pollution, representing less than 10% of all vehicles, but roughly 40% of their carbon emissions, and their activity keeps growing. Recent works in this domain have shown four main and promising zero-emission technologies: catenary or in-road charging electric, plug-in electric, hydrogen fuel cell vehicles, and e-fuels. Each technology offers the prospect of lowering carbon emission, no tailpipe emissions, and greater renewable energy use. Matching specific electric and hydrogen technologies to a particular truck segment can help overcome barriers such as traveling range, infrastructure, and recharging time. First, we will focus on electric road system. There are several forms of electric road system, including conductive and inductive systems. One of the most mature and cost-effective technologies was found to be overhead catenary system. Current image shows an overhead catenary system installed on a German highway. The overhead catenary system has been used in the railway sector before. It consists of a supporting structure built outside the road boundary that holds two cable systems. These wires supply the positive and negative electrical circuit that is picked up through a pantograph collector on the roof of the heavy goods vehicle. The pantograph can be rapidly connected and disconnected automatically as needed. The heavy goods vehicle is free to leave the wires to overtake or complete its journey away from the catenary using a separate onboard battery, approximately of the size of an electric car battery, providing zero tailpipe emissions at all times. During the transition period, it is anticipated that hybrid vehicles will combine catenary power with diesel, biogas, or hydrogen fuel cells to ensure necessary operational flexibility. As mentioned earlier, the second promising technology in attempts to decarbonize freight is using plug-in battery. Some of the barriers in implementing it in freight include limited range, battery cost, and charging time. To overcome some of the challenges, battery swapping technology could be used. Such an approach would require that truck accommodates multiple daily battery pack swaps. Battery swapping stations are deployed on key routes, and at a larger stock of battery packs is managed as a system. The time to replace the battery would then become competitive with refueling time, but they would still require more stops than conventional diesel if used on long-haul operation. Because of the infrastructure and system-level complexities, only a few projects have become operational. Since 2013, a fleet of electric buses in China has extensively utilized battery swapping. Next, fuel cells. They are also receiving significant attention as an option for medium and heavy-duty applications. Using hydrogen as their fuel source, fuel cell electric vehicles offer longer ranges with shorter refuel times compared to battery electric vehicle recharging. Fuel cell stacks capable of greater efficiency are much more efficient than diesel systems. Several studies have identified fuel cells as a potential solution to applications like suburban delivery trucks and shuttle buses, where flexibility and long range are needed. One estimate suggests that hydrogen fuel cell range extending motors become competitive with plug-in electric vehicles over 60 miles, although falling battery prices may affect this trade-off. Although they have great potential, hydrogen-powered vehicles will face multiple challenges, including high hydrogen costs, lack of refueling infrastructure, and low efficiency, which government interventions are seeking to overcome. Because of the high cost of fuel cell and hydrogen, some researchers calculate that fuel cell delivery vehicles have higher total cost of ownership compared to conventional hybrid or battery electric vehicles. As of right now, the comparison between long-distance fuel cell electric truck and battery electric truck could be interpreted as being in favor of battery electric truck. The total cost of ownership over 5 years user period is much higher for the fuel cell electric truck. In terms of maximum range, fuel cell electric truck is predicted to have substantially higher range at around 1200 kilometers as opposed to 800 kilometer range for battery electric truck. Refilling and charging time are much faster for fuel cell electric truck. However, fuel cell electric truck falls short in context of economies of scale with cars. To learn more about hydrogen vehicles, I invite you to watch clips that are indicated below this video. In the next video, we will discuss the last category of fuels that are classified as e-fuels or synthetic fuels.